Okay, so what's up mga ka-physics? Welcome to our second to the last topic for FS122 mid-year edition, which is radioactivity. Ang bilis ng panahon na magsi 6 weeks na tayo. And after nyan, first sem na naman. Alright. So, maraming controversial na topics sa food tech, no? Gaya ng mga GMOs, na parang ayaw kainin ng mga tao, gusto nila organic lang. And of course, one of the other controversial topics is irradiated food na baka, pag kinain ko yan, mag-mutate ba ako? Magkakaroon ako ng superpowers or magkaka-cancer lang ako? So, let's find out what radiation is, what are the different particles associated with food irradiation, and as well as other applications of radioactivity principles in food science. So stick with me to find out. Tara! So this is what radioactivity is not. Alright, so mag-definition of terms muna tayo, no? When you say something is radioactive, it simply means that there is an emission of high energy radiation, with radiation being defined as energy from electromagnetic waves or emitted as electromagnetic waves or moving subatomic particles. So either of the two is defined as radiation. So lumabas ka sa araw, magpa-araw ka, that is solar radiation, and theoretically radiation pa rin yun. Or right now, as you are sitting and watching this video, maraming klase ng radiation kahit nasa loob ka ng bahay na dumadaan sa katawan mo, yung radio waves, no, yung signal ng TV mo, yung mga UHF, etc., yung waves ng signal ng cellphone mo, etc., etc. So lahat yun ay radiation. Alright, so you're probably familiar also with the term isotopes, wherein atoms with the same number of protons have a different number of neutrons. So, for example, carbon has different isotopes. We know of the normal carbon-12 with 6 protons and 6 neutrons. There's also carbon-13 and 14 with 7 and 8 neutrons respectively. So you may have heard about this from when someone taught carbon dating. No? So there are assumptions about isotopes that they are usually unstable, no? Lalo na yung malayo dun sa normal na periodic table definition natin ng isang element. So when isotopes are unstable, they emit high energy particles or radiation without external influences. So ito yung tinatawag na activity na mag-isa silang nag-emit ng particles, meaning to say hindi mo kailangan ng external force, and as a matter of in a matter of time they will continuously emit yung particles na yon. Okay, all isotopes with greater than 83 protons are generally unstable radioisotopes. And then we also distinguish between natural and artificial radioactivity based on whether or not the isotopes are commonly found in nature or are fabricated using nuclear transformation methods. So here are examples of the half-lives of certain elements such as hydrogen-3, so on. So as you can see, medyo matagal ito, no? Years. Okay? And it could vary from 3-digit years to a million years. So we know that the concept of half-life is used to calculate certain parameters about your kung ano mang, let's say, food sample yon or material yung kinukunan mo ng properties, no? And we'll look at this a bit more. Right, so here's an overview of the different types of radiation. You have alpha, beta, gamma radiation, and neutron radiation or neutron emission. And ito yung charges nila ng radiated particles as well as their description. So there's a video after this slide that you can click to watch, and then we'll discuss each of the types of radiation afterwards. So as you can see from the video, the differences between the different types of radiation is the emitted particles, the range and speed, and how to stop them. So for alpha radiation, it has the shortest range and lowest speed and is the easiest to stop. And it generally emits two protons plus two neutrons, thus the positive charge and the relatively high mass. So an example of this is in alpha decay, as you can see here. You have your uranium degrading into thorium and helium. Okay, so the effect of this is strong ionizing effect in the nearby surroundings, wherein radiation energizes particles through bombardment while in transit. So yung mga natatamaan niya, and then the secondary particles become charged as well, turning into charge carriers. Thus, the term ionizing radiation. Beta radiation, on the other hand, emits either electrons or positrons at the speed of light, thus having a longer range and longer ionization effect than an alpha particle. An example again is uranium, um, which degrades into neptunium plus one electron. So electron decay in this case. Gamma decay, on the other hand, emits energy at the speed of light, with a longer range and ionizing effect on both alpha and beta radiation. And the frequency of electromagnetic waves is those above X-rays. So radioactive decay is actually an attempt to normalize itself na yung radioactive material because it wants to be stable. So to do that, it emits high amounts of energy to reduce the imbalance in the amount of protons and neutrons in the nucleus. The process of decay then is the reduction in radioactive strength over time, and the rate of decay is proportional to the radioactivity of the substance or the radio intensity and the amount of available nuclei, which is a function of course, the mass of the substance. It's also important in designing systems using controlled application of radiation, since hindi mo naman force yung decay, at least you know how fast the rate happens. Alright, so equations time na naman po tayo. Simple lang naman ito. So the rate of change of the amount of atoms as a function of time is equal to the initial number of atoms and the decay rate constant, which is a function of the material itself, a material constant. So, kaya po siya negative kasi nababawasan, right? So, and this term, the change in the number of atoms over time, is what we'll call your activity. So, pag mas maraming nababawas na atoms over time, then mas mataas yung activity mo, yung magnitude ng activity. Okay? And if, as usual, we integrate these, then we will get a relationship between the number of atoms, initial number of atoms, and time, no? So if we arrange this to get rid of the ln by using E, then based on the initial number of atoms, we can get the current number of atoms as a function of time using this equation. Current number of atoms is equal to initial number of atoms multiplied by e raised to the negative product of the decay constant and the time elapsed. So the half-life is defined simply as the time it takes for your n to be equal to half its original number. Okay, so if we substitute that for the equation from the previous slide, para makuha natin yung equation for half-life, then we can get half-life to be equal to negative ln 1 half multiplied by 1 over the decay rate constant. So we know, of course, that half-life is one of the useful isotope parameters that we could use, for a variety of different things. So we also have the specific activity denoted by the small letter a, which is simply defined as activity per unit mass of the material, or capital letter A, over the total mass. Okay, and with an SI unit of becquerels per kilogram, where the becquerel is a measure of the number of nuclear or radioactive materials decaying per second. So therefore, ang base SI unit ng becquerel ay 1 over second, na parang frequency yung hertz, 1 over second din. Pero ang binibilang mo ngayon dito is actually number of nuclei. Okay, and then if you have heterogeneous mixtures of multiple radioactive substances, then the specific activity for that mixture would be the total activity divided by the total mass. And then based on the definition of the activity, therefore it is then equal to your activity over mass, lambda n. So lambda multiplied by Na over the total mass. So activity per unit mass in a way is important because it allows us to gauge how much energy in a way can be released indirectly. No? So in this case, for example, 1 gram of radium during its lifespan of emitting radioactive energy can emit a total of 1.2 times 10 raised to the 7 kilojoules. So I did some quick math, and for an average household, that would amount to 16 months household consumption. And this is one of the reasons why, for example, nuclear submarines can go for years without refueling, with just how much uranium on board to power everything they need, no? Because they have to stay underwater for very long periods of time, and therefore wala namang gas station sa gitna ng dagat. Well, anyway, of course they need to restock on food supply through a supply ship. Tayo napunta sa submarines anyway. So yeah, this table shows us an example of the decay constant and consequently the half-lives of certain radioactive materials. So as you can see, kapag yung decay constant mo ay mas malaki, mas maliit din yung half-life mo. And again, the difference in half-lives of isotopes are exponential in magnitude, anywhere from days to, what is this, 1 billion years, no? So we mentioned earlier that one effect of these emitted particles is that these are ionizing radiation, which could cause ionization of secondary particles. It bombards, no? So we need to be able to measure the amount of ionizing radiation, and this measurement is, or detection of the amount of ionizing radiation, is based on detecting the effects of the ionization. Okay, so we determine the amount of ions produced through excitation detectors. And to filter between alpha, beta, and gamma radiation, we could use the following methods, no? Either magnetic fields that separate particles, electrons, positrons, and or using blocking of alpha and beta to, let's say, isolate gamma radiation using different materials such as metal sheets or materials that can block alpha radiation within a certain thickness of it. So we have what we call counting tubes, or also Geiger counters, not to be confused with those used in the anime Dragon Ball to count the power level of their opponents. Kung nanood man kayo nung kabataan nyo. So how does this work? Ions are produced by passing radiation through noble gases, and then the strong electric field supplied rather causes further impact on ionizing um, secondary particles. And then when the gas atoms are further excited, they dissolve photoelectrons on the tube wall. And finally, an avalanche of electrons measured as a short pulse of electric current can be translated into a measure of ionizing radiation. So in the next slides are links to videos you could watch to visualize this process. So there are also semiconductor detectors which um, translate the ions produced by radioactive radiation to countable voltage pulses in a semiconductor detector. And the advantage of this one is that it's possible to profile um, multiple parameters such as radiation decay, frequency, quantity, and even the energy spectrum, which in turn can allow us to identify the type of radiation and source. So again, para siyang pag-fingerprint din ng radiation mo. Okay, and here's an example of the energy spectrum. So the intensity is plotted versus the energy. Okay, yeah, so may peaks ka. Okay, so trivia, in case you didn't know, the human body is actually radioactive. So if, for example, if you look at potassium 40 alone, which is a radioactive substance, it contributes to the specific radioactivity of the body with a radioactivity of 130 becquerels per kilogram of body mass. So there are also other radionucleotides in the body, okay, as you can see here, and that gives us a total radioactivity, of course, depending on your mass. So actually, yan pwede mong sabihin sa kaibigan mo, uy, alam mo ba radioactive ka? Okay, trivia lang. So more trivia, hindi lang naman tawag dito, hindi lang naman katawan natin yung radioactive. Of course, kung potassium ay radioactive, then yung foods na may potassium can also be radioactive. Okay, granted, we don't eat fertilizer, but we know that fertilizer has a lot of potassium. Kasi nga, potassium nitrate siya. Okay. Yan, as you can see, there are lots of radioactive foods naturally occurring. So even if these were organic foods, as long as they contain potassium, it's likely that they would have radioactive potassium included, no? Kasi lahat naman ng isotopes ay distributed. So, hindi mo may iwasan kumain ng radioactive materials in food. Ang tanong is how much and what really is the effect, no, sa atin. So definitely, exposure to radiation may have negative impact, but yun nga, ang tanong is yung amount, which is a matter of maybe length of exposure and gaano kalakas yung radiation na yun. And in terms of ionizing radiation, the effect is measured in the amount of ionizing radiation absorbed with the body multiplied by that quote-unquote quality of ionizing radiation determined through a quality factor. Okay, so the general equation is that the absorbed dose is equal to the energy of radiation over the mass of the body. Okay, and we also have a dose equivalent na tinatawag, which is quality factor multiplied by this absorbed dose of ionizing radiation. And usually we use the term gray to denote that absorbed energy of radiation over mass in joules per kilogram. Okay? And as you can see here, ito yung example ng quality factors mo. So, di ba, kaya pala pag sa nag-X-ray ka, pinapasuot ka ng isang radiation shield, and of course, they limit yung exposure mo to X-ray. Although, of course, as you can see here, the quality factor is among the lowest, same with beta radiation and gamma radiation. However, when it comes to neutrons, depending kung ilang kilo electron volts or mega electron volts, no, kung gaano ka taas yung quality factor. And then for protons and alpha particles, mataas din. Although alpha particles are very easily blocked, no, even by, again, a piece of paper. So, unless you're in direct contact at nakahubad ka, pero even then, it would only contact mostly your skin. Okay, so you just might want to pause this slide to try and read through this handy reference for some of the equations we've discussed, and it's their equivalent SI unit and more common definitions of the SI units. Okay. Finally, after much build-up, andito na tayo sa main application, which is food irradiation, wherein we use beta and gamma particles of gamma radiation to both food and packaging materials. It is a form of non-thermal treatment, which has various effects, ultimately leading to longer shelf life while retaining the quality of the food. So, as you can see here, in terms of kilogray, ito yung mga effects niya. So even a small amount is lethal to the human body, and that is why food irradiation, of course, is done in enclosed chambers or pretty much away from human exposure through the use of materials that could block said radiation. Other effects include as follows, no? Sprout inhibition, pest control or disrupting insects, ripening control, pathogenic destruction or sterilization, and then virus and enzyme inactivation. So, pwede palang gamitin to sa COVID-19. Good luck sa pag-target, no? Kasi nasa katawan ng tao, patay ka muna bago mapatay yung virus. So the inactivation of microorganisms happens through the action of free radicals formed during ionization, which interrupts the cell division. So can't multiply, they become extinct. Okay, beta radiation is produced through linear accelerators, while gamma radiation is derived from radioactive sources such as cobalt-60. Because of gamma radiation's greater penetrating power, then a greater amount of shielding would be needed to protect from exposure. Typical storage would be under 4 meters of water or having a 15 centimeter thick cabinet of lead. Ano ba yun? 15 cm. Alam niyo pala yun from FS 131, no? Yung 150 mm scale, yung ganon, kakapal. Alright. And even the treatment chamber is shielded in this case by 2-meter concrete walls. So that's taller probably than the tallest person in class. Pahigain nyo, ganun kakapal yung semento, kulang pa yun. Okay, so definitely because of the negative effects, its use is controlled in terms of applications, and depending on where we live in this planet, there may be regulations restricting its use. Like for the US, at the very least may labeling law sila na kailangan sabihin mong irradiated yung pagkain dahil may concern yung mga tao na hindi naniniwala na safe siya or what. If you have a conveyor belt system, then that would determine the length of exposure to the radiation kasi constant speed naman yon, nadadaan siya dun sa path kung saan na nagaganap yung ionization. Contrary to popular notion, foods do not become radioactive when exposed to ionizing radiation. So all of the effects on the previous slide can happen but not cause the food to also have radioactive decay. So, pero kung yung food na yun, like may potassium siya, may isotope, o radioactive na siya to start with, but exposure to radiation will not increase, say, that amount of initial radioactivity it already has. Then if there's one possible side effect, if the amount of energy used is below 10 mega electron volts, then there could be a free radical formation. So here's an example of how it would look like. So yun yung radiation source underwater, and then meron kang parang mga conveyor belt system dito containing what is to be irradiated. Then you have a loading and unloading. Okay, so para lang siyang what? Carnival rides pero foods yung laman yan. So the Philippine Nuclear Research Institute under the DOST actually has an irradiation facility. You can watch the video in the link below. No, they rent it out for small commercial irradiation purposes. And dahil medyo maliit nga yung scale, typically reserved dito sa kung hindi pharmaceuticals, I think may gumagamit din ito sa mga herbal yung mga powders, no? So, and you can watch the video there to find out more about it. What are the other effects of food irradiation on our proximate components or food molecules? So for protein, there is the denaturation that can be similar to how it denatures through heat or acids. Which is through the splitting of peptide molecules, thus altering viscosity. And irradiation products like amines and sulfur volatiles, however, may degrade food quality. So you might have to control radiation here. For fats, oxidation could happen and the formation of carbonyls and peroxides, while for starch, hydrolysis of the high molecular weight compounds could happen, such as your dextrins, amylose, and amylopectins. The ultimate result of this is decrease in viscosity and firmness. So food irradiation is widely applied in a large scale in the US, and though they're supposed to have this seal to identify the food as being irradiated. Pero ito at least you can see they're applied to fresh produce and frozen produce as well as juices. Okay, so there are other so many methods you can use to detect radiation for whatever purpose it may serve, and these include electron spin resonance spectroscopy and paramagnetic resonance through the determination of free radicals, and thermoluminescence, wherein the changes in the crystal lattice of irradiation food allows for photon emission, which can be detected during heating. And there are also other methods such as optical simulated luminescence. You can also use DSC, HPLC, and GC as well. So we will not go into the specifics of how, but of course, if you want to, you could always do some further reading. Just so you know, there are many methods you could use if you want to identify if food has been irradiated. As a prelude to our next topic, which is sensors, there are also ways in which you can use radioactivity to measure different things. No, a simple example is using beta absorption to measure in real time the thickness of produced vapors, polymers, and metals. Okay, or gamma absorption to measure the thickness of glass, metals, and polymers, etc. Okay. So these are likely based on transmission, no? Detect kapag mas makapal, halimbawa, mas less yung tatagos na radiation, and then they measure that. So then you could also use backscattering to measure the thickness of thin films in the production of packaging materials. Okay, and there's also a use for when you blow ionized air to eliminate the static electric charge from hardware parts, because as you know, itong mga electronics ay kailangan free from static electricity. Okay. There's also an electron capture detector used in gas chromatography, which could measure electron current from during analysis. We can also use beta radiography to image organs in medical applications, and even in the inspection of authenticity of bank notes. Gamma radiography, on the other hand, can be used for inspection of welded materials. So mostly may food and non-food applications nito, no? And other forms of radiography for materials with low mass number, and other forms of other applications of irradiation, such as for sterilization of medical devices, tumor treatment, and treatment of course, food products. So in this case now, we can see na yung application ng radioactivity also includes packaging materials and as sensors, and not just as a process. But nonetheless, these are all based on food irradiation principles and the principle of ionizing radiation and its effects on food. So here are just some additional videos you could watch, no? And see for yourself kung ano pa yung global impacts ng food irradiation and even how it helps climate change.